Hey everybody, in this tutorial I'm going to show you how to use Unity's animation rigging system to create an IK constraint on a model with any number of legs so that its feet match the position and angle of the terrain. These models already have animations on them. You can see them walking here. The one on the left does not have any rigging set up. And you can see his left feet just kind of sink into the ground and his right feet are floating. Whereas this model, he's on this little crevice here, and each of the feet is matching the position and the angle of the terrain. That is our ultimate goal here. Towards the end, once we get the feet set up, I'll also set up the body rotation based on the average of the feet, as well as the capsule collider movement, so that if he's too low or too high off the ground, the capsule collider will just move to compensate. Okay, so I actually forgot to show earlier, before I started scripting, I got ahead of myself, but I can actually show you the how this is going to work at the end of it. So if we go ahead and hit play here, and I'm actually going to move my game screen over. So now you can see as my dragon is sitting in this crevice here, the red one, his feet are turned to match the terrain, which is exactly what we want. Also, you can note that as he's walking, it should move, and his body changes position as well. We'll be changing, just rotating the character's body based on the normals of all the feet kind of averaged. So then I can just have my little dragon walk around, and his feet will match the terrain as he goes, and his body will rotate as well. And a good extreme example that I like to show is if I have him over here on this ledge. Now look at this. He's sitting here, and 3/4 of his body, including his collider, is below this ledge, but his foot is above it. He's kind of hanging over it, and he's kind of creeping a little bit. But that's exactly what we want. Instead of sinking into the ground or floating, he's not floating over here, or his foot isn't sinking in. It's exactly on this ledge, which is perfect. And then I can have him move around some more. He can bang his head into the ground for a second there. And then here I can have him just kind of stand here, all his feet match the terrain, and it's exactly what we want. To get started, you're going to need to set up a bone renderer on your dragon. I've already got one here. It's quite simply going up to animation rigging and bone renderer set up on your model. After that, you want to put a rig on your guy here, and then there's going to be one 2-bone IK constraint for each limb, and you have your upper, your middle, and your foot for the root, the mid, and the tip. And then you want to have a target, and each of these targets is at the world placement of the foot here. So I can zoom in here. So 0, 0, and here, let me open this up. So 0, 0 of his hand is exactly where this target is. And that's exactly what you want. Once you've got those set up, we're going to go and initialize or go into our IK foot behavior script. I don't have anything in it right now, just so I can go over it with you. I do have a cheat sheet. Since I'm new to making tutorials and everything, I'm probably going to be looking over at it and making sure I'm typing the right things. But I'll be typing and trying to explain everything as I go here while you're watching. So first you need to include the Unity Animations rigging reference here. So Unity Engine, actually. Animations and rigging. Without that, a lot of the IK bone constraint behavior that you're going to be modifying later won't be picked up, so you need to include that. Okay, next we're going to include references to each of the foot transforms and each of the target transforms, because we're going to be tracking the feet and modifying the targets. So we can do serialized field to make this easy to input. Call it a private transform, and it's the foot transform RF. And I don't know, I didn't really talk about it, but if you noticed here on my rigging system that I've got set up, I have right front, right back, and left front. And really for everything in the code and everything here in the editor, I'm going to be labeling them in that order just so that it stays consistent, and as well as for some looping that we're doing, that it's always getting the right foot and the right target together as well with the IK bone constraint that it's modifying. So kind of looking at it from the top here, you start right front and you just go clockwise around it. Okay, so I'm just going to take this guy. I'm going to copy him like that. And I'm actually just going to change these, and I typed them at the end so that it's easy to change everything all at once. And then I'm going to make a new array that will house each of these transforms. So private transform. Those little brackets are signaling that it's going to be an array, and we're going to call it all foot transforms. Okay, then we're also going to do the same thing for the targets. Transform foot target transform RF. Okay, just copy and paste that a bunch of times. Left back, left front. Okay, and then another array. Oh, didn't mean to do that. And then another private array of transforms housing all these targets. So all foot, target transforms. Okay. So now I'm going to save this real quick. I'm going to go back to my editor, and I'm just going to paste all these in to this script using that serializable field. So here we've got right front, left back, left front, and same for the targets. So now I'm just going to find all of my arms, or I guess legs in this case, and I'm going to paste them in. So the hand is the right front, the other hand is left front, and then the foot on the left and the foot on the right. You could find these via child, finding each of the child all the way down from the root. I just use serialized field here to make it easy on myself, click and drag. So same here, right front, right back, left front, or left back and left front. Okay. So those are all inputted now, and we can reference them and we can change them as we need to. All right. So in our start, and here I changed this to fixed update. Instead of update, I want it to match the framing of the physics engine, not the frame rate of whatever system you're running off of. In my opinion, for something like this, where you may be changing the physics and the positioning of your object, you don't want it to speed up or slow down based on your system. So that's why I'm doing fixed update. So in my start method here, I'm just going to initialize these two arrays and then input all of these transforms into the array for looping purposes later. So to initialize the array, you just type the variable name and you set it equal to a new whatever type it is, whatever variable type it is, and then you just say how big it is. So it's for large. And same with the foot targets. And then for each of these array elements, we're going to just input, whatever particular transform it is. And I'm just going to go down the line. So you can now say all foot targets, or all foot transforms rather, 0 is equal to foot transform right front. Okay, and then I'm going to paste this a bunch of times, and then it's right back, left front, and the 0th element, the first, the second, and the third. That does bug me coming from just starting with a 0th element for a lot of programming languages has always bugged me because there's 4 elements, but your last element is the third. It's just silly to me, but you know, it's whatever. All right, so now we do all the transforms for the targets. Same thing, 0th. And so notice how here I want my target for the same foot. So starting with right front, then right back, left front. That way when we're looping, it's all the correct target for the correct foot. Okay. All right, after this, going to go ahead and initialize now all of our IK constraints. Later on, we're going to be taking these, and here, let me let Unity compile. Later on, we're going to be changing these weights based on our little dragon's animation cycle. So when his foot is in the air, and I can actually, let's put his walking animation just so it can go, and you can see. And let me actually change these to this one to 0 so you can see. So right now, all the rest of the weights, and you can see already that, you know, since we've got these targets in here, they're not allowing the feet to move because their weights are all the way up. With this weight being 0, you can see, you know, he's not moving anywhere, but his animation is having him pick up his foot as, you know, like he's walking. So later on, we're going to be changing these weights based on his animation. We're going to go into his animator and we're going to match, you know, frame by frame almost. I'm going to pick a few keyframes and say when his foot is on the ground in this animation, the weight needs to be high. And when it's in the air, it needs to be close to 0, if not 0. That way he can still pick his foot up. Because as you can see here, if I change this now back to 1, he can't even pick his foot up. So now we're just going to initialize all of these two-bone IK constraints in our script so that we can reference this weight and change it as we go. All right, so we can pause that here. Change it back to idle for now. Okay, so in order to get all of the these two-bone IK constraint scripts essentially and be able to modify these values, now we have to take all these placements and placement rigs and put them into our script as well. And I'm going to use the same method that I did before, where I'm going to serialize a field and I'm just going to label it and then drag and drop it. Okay, so we're going to do serialize field again, and it's going to be a private game object, and we're going to call this foot rig RF. And this will be each element that contains our IK constraint values and script essentially. I'm going to smack the mic by accident. Hopefully I can fix that. And then we're going to initialize another array, because as we're looping through, we're going to be modifying the weights of the IK constraint for each foot individually. So I'm going to make another array, call it oh, and since you're using these this animation rigging package, now you can actually call an object called two-bone IK constraint. It knows what that is because it's a script in there. So now we're going to initialize it here. All foot IK constraints is equal to new two-bone IK constraints array of the size 4. And now each of these array elements is going to be equal to a rig of each of the feet. So foot rig RF. I'm going to save this. Right back, and left front. Oh, I'm sorry. We need to get the components for each of these. It's not the rig itself. It's a component. So off of this game object, we're now getting its 2-bone IK constraint. There we go. All right, now it's happy. So now we're pulling in the rig and we're getting its component, and then later on we're going to be modifying those weights. So actually, let me go into Unity here. It's going to compile because we saved it. And now we just drag and drop each of the rigs in order. So right front, right back, left back, and left front. The naming here is not as, it's not super important. You can name it whatever you want as long as you know what it is. And I suppose that's really true for most things here. All right, let's actually exit play. I don't know why it's been playing the whole time. And because it's been playing, and I had set it up to be blue so that I'd know when it's playing, and I didn't notice. So we have to do this again. Okay, now we have all these rigs in here, and in each of these rigs they have this 2-bone IK constraint with their proper, leg here, or arm. I suppose they called it an arm and a leg, but these are all legs. And so now later on we can actually modify these weights directly in the script and match it to our model walking animation. The first method that we're going to add in here is a sphere cast method. It will just take the regular sphere cast, add in some additional bits and bobs onto it, and output exactly what we're going to want. So I'm going to call it private void check ground below. Okay. And since this is just basically a modified sphere cast, our inputs and outputs are going to be very similar. So I'm going to list them out here now. We want to output a vector 3. We're going to call it hit point. We're going to output a Boolean called got ground spherecast hit. I'm going to output a vector 3 called hit normal. Output a layer mask and call that hit layer. Output a float called current hit distance. And then our inputs, there's going to be 4. First we need the transform of the object that we're checking below. Then we need an integer, which is our layer mask that we're checking for. So in this instance, it's going to be the ground. Theoretically, you could use check for any layer mask. We need to label our max hit distance for this sphere cast, how far the sphere is going to go before it stops, if it hasn't anything. And then finally a float, and this one's going to be called added height. And I'll explain it a little better later on. Okay, so a sphere cast on its own will output a Boolean. Basically it will output a true if it hits something and a false if it doesn't. And we can use that to our advantage here, so we can set up an if statement and just call it if physics dot spherecast else here. And so what we're going to do here is we're going to set up our outputs if we do get a sphere cast hit, and then kind of set up nulls if we don't. So in the sphere cast, we're going to, its origin is going to be called start sphere cast. Its radius, I'm going to use 0.2f. That's essentially just, The radius of the sphere, I personally kind of matched it to the ankle radius, just through trial and error here. But the reason we're doing a sphere cast instead of a ray cast is because this foot has, it's larger than just a single point. If there is a little crevice that the foot wouldn't fit in, but it's over top of, if we used a ray cast, then that ray cast would say, oh yeah, we're gonna put the target, the hit is going to be at the bottom of this crevice, and that's where the target's going to go. And then that foot is just going to sink into the ground because of that little crevice. So the sphere cast helps us prevent that. It'll just stop at something that is about the size of its ankle. Okay, the direction of the sphere cast is always going to just be down. We're going to output a hit, not a hit layer. Going to output a hit. Going to input the max hit distance. Going to input our layer mask that we're checking for. And then the query trigger interaction, we're just going to use the global. Okay. So you're probably wondering what the start sphere cast is and a few other things. So because we want to be able to place the foot onto the ground, but continue sphere casting and not go through the ground, we need this added height here. And this added height is going to just take that sphere cast. We're going to start it at the origin of the foot plus some distance. So that way, if the foot is on the ground, it's still going to start above the ground and go down and hit the ground, not start at the ground and then go below it. Because a sphere cast, if it starts, basically on top of what you're looking for, it'll just pass right through it. So we need a vector 3 for the start sphere cast. And all we're going to do is do object transform dot position, and that's going to be our foot transform, foot position. And then add in new vector 3. We don't need to add anything in the X or the Z, but we do want to add in this added height here. That way its starting point is always just the origin of the foot plus in the Y direction, whatever added height that we specify. For this hit, it's just you use a raycast hit and just call it hit. And that just allows it to output exactly what you need, that information from this hit. If it's a raycast or a sphere cast, it's always going to output things like the position of where it hit, this distance that it went, and the normal of the object that it hit. And so this is just how we initialize that. And then at the start of our method here, we're just going to set this sphere cast hit to false. That way, if actually, you know what? I'm going to just put it at the beginning. I'm going to do else here. And then also we need another if statement here, and I'll explain this momentarily. This is actually going to be else. Okay, I apologize. I made a bit of a jump there, but I'll explain it here real quick. So when we're checking for a layer mask, there's a bit of stuff we need to do first in order for this sphere cast to know exactly what layer we need. It's a little bit confusing to me, the syntax of it, but I found this through some searching online, and it seems to work very, very well. And so that's what we're going to use here. So up at the start, we're going to look for a ground layer mask and call layer mask, name to layer, and look for ground. And all this is just whatever you're labeling your ground or whatever you're looking for here. So in my case, if I click on my cube here, that's below these guys, it's layer ground. And I also actually need to initialize this here. So we're going to call private layer mask ground layer mask. Okay. Now, if I misspelled it and called it grund, this name to layer would actually return -1, saying, all right, you looked for a layer named grund and it doesn't exist. And so -1 just means there is no layer with that name. And so we want to put an if statement in here saying if there's a -1, if you're trying to search for a layer that doesn't exist, just output an error. That way we know we can go and debug and fix what we're looking for. So here, we're just going to check for layer mask. And if that check for layer mask is equal to -1, we're just going to output a debug.log error and say layer does not exist. Then we're also going to output some basically null values for this sphere cast. That way it can still output and it doesn't give an error for this check ground below method itself. So current hit distance, that's going to be equal to 0. Our hit layer is going to be equal to layer mask name to layer, and we're just going to say it's going to be player. That way, if it doesn't hit anything, it's just hitting the quote-unquote player, even though it's not looking for it. That tells us, it's not hitting anything. Hit normal is going to be vector3 up, just straight up away from the XZ plane of the world. And the hit point, that's going to be equal to the original object transform that we started at. That way it's just where the foot is. Okay, and we can also take this sphere cast hit, set that equal to false here, and then take all of these and put them here as well. That way, if we, for some reason, aren't checking for the right layer mask, it doesn't exist, we'll get kind of our null values. Or if our sphere cast doesn't actually hit anything, we'll get our null values as well. Before we do this, we need to initialize this layer mask. And this is going to be an integer called layer mask. And that's going to be equal to 1 less than check for layer mask. And this will tell the sphere cast to check for exactly only this layer mask. It's going to check for ground and nothing else. Okay, now if we do hit, if our sphere cast does hit something, we want to output all those values so we can use them later. So the hit layer. And right now, since we're only ever checking for ground, this doesn't matter as much. But if we were checking for ground or a castle or an enemy, and you want to be able to stand on top of your enemy, you would want to keep this. So that's why I'm putting it in here for future use. We're going to output that layer. The current hit distance, that's going to be equal to that hit distance minus the added height. So that even though we're starting the sphere cast above the foot, now we're subtracting that out, so we're actually getting the total distance from the foot to the ground and not that added height. Okay. Now our hit normal is equal to hit.normal. Pretty simple. Our got ground sphere cast hit is equal to true. And our hit point is equal to hit.point. Okay. And now we have our check ground below method that, given the right inputs of our how far we want this thing to go, what the added height is, what layer mask we're checking for, or layer masks, you can check for multiple at a time, and then that starting transform, we can get all this information out. Okay, because for this particular model, I'm always going to be using the same added height and max distance. I'm just going to initialize them up top. If you wanted to, you could leave those as public variables, or change them as you went if you're using different models or anything like that. But I'm just going to start it up here. So it's going to be a private float max hit distance. That's going to be equal to 5, and private float height is equal to 3f. Okay, so that's all good. Okay, so you're probably wondering, why did I say 3 and 5? So I can go to my model here. If Unity would compile, there we go. Okay. Now I'm going to change him back to idle. So if I hit play here, actually he's got no gravity right now, so I can move him up. I'm going to move him up, and I'm going to take a target, I'm going to move it in and move it down. So now I'm getting his, from the top of the shoulder all the way down to the foot, that total distance. And here we've got about -1-ish. And then going up to the shoulder, we get a +2, positive 1.5. So I'm going to round up to 3. So roughly, a little less, but roughly from the top of his shoulder down to his foot is about 3. So I wanted that to be my added height. And then our max distance is just going to be this added height. So starting at if his foot is all the way stretched, and then adding an additional 2 here. So that is as far as our sphere cast is going to go. You can modify that if you don't want him, checking for the ground this far, if you want it to be half that, or, only that distance. I just found that additional distance kind of helps later on. So we're going to turn that off. I'm going to go back over here. So that's where these came in. Okay. All right, now we're going to create 2 more methods. And these methods are pretty small, but they're for checking the angle of the ground, and then taking the original X and Z axes of our targets and projecting them onto the ground so that our new X and Z are angled properly to be in line with a theoretical X and Z of the ground. So let me pull these up here on my other screen, my cheat sheet. So the first one is going to be a vector 3 method. We're going to call this project on contact plane. And this particular little method I stole from a website. I guess it's sort of a dev blog, but called Cat-like Coding. I'll put a link in the description for his website as well. He helped me with some movement scripts, and I am plagiarizing his simple method here. So I just wanted to give a shout out to him. Cat-like Coding, I believe. I'll put a link in the description. So here we're going to return a vector. No, not a vector. Minus hit normal times vector 3 dot. It's a dot product. Vector and the hit normal. That's what it's going to return. The inputs are going to be a vector 3 called vector and a vector 3 called hit normal. So then later on, our input vector is going to be our forward and our right of each individual foot, and our hit normal is just going to be the hit normal coming off of this sphere cast. The other method we need now is getting that angle between the original the original axis, the front and the right, and the new projected axis. So we're going to call this private void projected axis angles. And this is going to output a float called angle about x, output a float called angle up about z, and we need to input a transform, and we'll just call this target trans. We'll just call this transform, actually. Transform. Actually, we already have a transform in here, so we don't want to do that. We'll call this foot target transform, because that's what we're using, and we're being very literal here. So hit normal is our other input. So now what we want to do is take a vector 3 and call this x-axis projected, and it's going to call this other method that we just made called project on contact plane. And then we want to input our foot target transform, and we actually don't need RF because we labeled it here. And then we want the forward, and then we are projecting it onto the plane created from the hit normal. So now hit normal, and then we're going to normalize this because we're trying to use our new vector as an axis. We want the total magnitude of the vector to still be equal to 1, so we need to normalize it. Now I'm actually going to just copy this, change it to z. Okay, now we need to get our outputs. So angle about x is going to be equal to vector call vector 3, and then get the signed angle. And all this is doing is you give it 2 vectors, and it gives the angle between them. And the reason we want to sign it is if we're going down, if we're starting with a vector that's going up and we want to angle it down, we need one sign. And if we're going the opposite way, we need the other sign. And that'll help us rotate the foot targets later. So foot target transform dot forward. And then we need our x-axis project. Actually, I'm going to change this. A little tip, if you don't know, if you want to rename in Visual Studio, if you want to rename everything of a variable, you just hold down Control, hit R twice, and then that will allow you to, and then you also need to use the arrow keys to not have it redo everything. But now you can see it changed it in both places, and just hit enter. I'm going to call it projected because it's projected on there. And then finally, you need to give it the vector at about which it's rotating. So in this case, the x and the z are going to be rotated about each other. And if I'm feeling, well, no, it's okay. All right, so foot target transform dot right. No, that's not what I wanted. And then we're just going to change everything here to be the opposite. And now this is Z. Oh, goodness gracious. I'm so sorry. Okay. I'm going to have to fix that. Okay, so now we have just kind of 2 small methods that we're going to be calling that will take our x and our z of the targets and the feet and project them onto the ground. So first of all, it's going to be another private void, and we're going to call this rotate character feet. And it doesn't have any inputs because it's going to be all self-contained. And before I forget, I need to take this method and actually put it in our fixed update so it's called every time. Okay. So now we need to be able to sphere cast below each foot and return that information and then use that hit normal and the max hit distance to tell us exactly where that target needs to go and at what angle that target needs to be rotated so that the foot matches the terrain. Okay. So first we're going to do a for loop. Because we created each foot, target, and rig into an array, and we labeled them all correctly with, say, the right front being 0 on all of them, and so on. We can now just create a for loop to loop through each foot. So if you had 18 feet for a weird boss monster, you can just, as long as you initialize it with all 18 feet, you can then just create this loop once, and it will do it for every single foot, which is great. So we're going to create a for loop. And we're just going to loop it 4 times. And each time we loop, we just increase it by 1. Okay. Now, first thing for each foot is we need to check the ground below it. So I'm actually going to, because I named these things all very similar. Well, no, it's okay. I can just type it all out. First, we want to output a vector 3 and call this hit point like we did before. We're going to output check ground below. Oh, I'm sorry. No. We're actually going to create another array of all the ground sphere casts. Forgot to do that earlier. I'll do that now. So we want to, later on, when we're rotating the character body, we're going to be checking all of the ground sphere casts to make sure they all hit. And if they all did, rotate the character body to be the average of all of them. So then I want to create a new vector up here. Call this private. It's going to be a Boolean array. And it's all ground sphere cast hits. And then we need to initialize it here. So all ground sphere cast hits is going to be equal to a new Boolean of size 5. And this is going to be each foot plus 1 for the body. Okay. And so now that we've done that, now we can say, for each foot, it's going to be I. That changes each time. That way it's just looping through 0 through 3 for each foot here and changing that sphere cast Boolean individually. Then we're also going to output a vector 3, call this hit normal. We're going to output the hit layer. And then we're actually going to ignore for now the current hit distance. We're going to input each of the foot transforms individually one by one. So do that I. We need to input our ground layer mask. And then we need to input this max hit distance and the added height. Okay, so I want to output a hit layer, so I'll just instantiate it here. I'm going to create a private layer mask. Call that hit layer. It's not super important at the moment, but I just want this in here anyways for future use. Okay, another thing we want to do, similar to the sphere casts creating an array of those, we're going to create an array of the hit normals. so that each hit normal can be added into the array every single time this thing is going to loop through. And then we can use that later on to average all of those hit normals to get the hit normal for the body. That way, if he's standing on top of a, the edge of a, here, if this can load. If he's standing right over on the edge of a crevice here, some of his feet are going down on this side, some of his other feet are going to be angled this way. The average is going to give us the body angle. Okay. Another variable to create. It's going to be a private vector3. It's going to be a array, and call this all hit normals. And this is just going to be very similar here. So new vector3, and it's array of size 4 because it's for each and every foot. Okay, so now for each time we loop, we're going to update this hit normal for each foot to be equal to the hit normal. All right, cool. Now we want to change the target if it hits something. So, and you could just say, all right, well, it's already giving us the null values if it's not hitting anything, so it's fine. But for right now, I'm going to actually have another if loop here that changes based on if the sphere cast hits something, and if not, we're just going to nullify that rotation and position. Actually, it needs to be true. And then if it doesn't happen, it's going to be false. So if we do end up hitting something for the sphere cast on that individual foot, we'll do something. We'll change the target position and rotation. If it doesn't, we just want it to be equal to where the foot is so that the foot can continue on its animation without being impeded. So now we're going to change the target transform position, if it's not hitting something, to be equal to all foot transforms dot I dot position, and the all target transforms. I'm actually, to make this a little less confusing, I'm just going to call it all target transforms and not all foot target transforms. And then we want to change the rotation to be equal to the rotation of the foot. Okay. It doesn't seem to be liking that because I said position instead of rotation. That would make sense. Okay, so that's what's going to happen if there is no hit on the sphere cast. If there is a hit, we want to take that target and we want to put it to the ground as well as rotate it to the ground to match the ground. So we need to find the difference in angle between the projected x-axis and the starting x-axis. So we're going to use our new method that we just generated and call projected axis angles. We're going to output the angle about x and out the angle about z. We want to input the foot transform that we're looping through at this point for the for loop, and we want to output the hit normal. And you could say all hit normals I, and put that here, and actually that is what I'm going to do. In this case though, every time you loop through here, hit normal will be replaced, so technically you could use either one. So I'll actually go ahead and change that to all hit normals, and okay. And I actually want to initiate the angle about X and Z since we're going to be outputting it there. So they are both floats. Okay, so it won't be mad at me anymore. There we go. Okay, so now we are going to take those angles. And now we want to move the target to the angle and position of based on the ground sphere cast. And you could say, hey, we want to take this hit point and we just want to use that to exactly center the target. But because our model already has animations on it, we actually want to use the model X and Z to determine where the target's going to be, and then just get the Y value out of that hit point so that the foot can match the ground in terms of height off of, or height for the Y, but then the X and Z is determined by that animation primarily. So I'm going to go ahead and say all target transforms I dot position. We're changing the position first. And that's going to be equal to a new vector 3. So like I just said, you want to match it to the foot in X and Z. So all foot transforms dot position dot X. And we'll do the Y momentarily. All foot transforms position dot Z. Okay, for the Y, first we want the hit point dot Y, but then now also we want to add an offset, and we're going to call it Y offset. This is so that if we go here to our model, maybe, there we go. If you look at the foot transform, you can see that 0, 0 of the foot, and kind of, let me move the skeleton there so you can actually see it. 0, 0 of the foot is actually kind of starting at the bottom of the ankle, not the bottom of the foot. And so this offset, you're just going to add a small amount to here so that the target goes to the ground and not just above it. Or actually, I'm sorry, you want it to go just above it so that this ankle snaps to the target just above the ground, and then the foot is on the ground. So I can actually take this left front, or no, I'm sorry, right front, and it's at 0.22 here. If I move it down to the bottom of the foot, it's almost 0 here. So I'm actually going to round down a little bit. So my Y offset, and I'll actually go ahead and set it up here. It's going to be another private float. Y offset is equal to 0.15. That's what I'm going to set it to, a little less than the 0.22. And that's just enough to where, say, the squishiness of the pad of his foot is being taken into account, even though it doesn't squish. In my experience, it helps it look a little more real and float a little less above the ground. Okay, so now actually we have this position here, and I'm going to save this. And we can go ahead and test it out here. We can see, if I go back to the model here. Okay. And his gravity's off so that I can pull him up here. Go ahead and hit play. So now if I lift him up, his feet are sticking to the ground. Or at least they're trying to if he's too high. And then once he gets too high, they just snap back down to, the targets snap to the feet. So it goes down, And then I can move him around, and then say if I move him over this crevice here, you can see the target's following the ground as close as I can, so I can actually move him down. And his feet will continue to follow that path. And that's great. That's exactly what we want. And now we can include the rotation as well. The rotation is going to be a little more in depth here. First, I want to reset the the target transform rotation. I'm going to reset this to be equal to the foot transform rotation. I found that as I was testing this, if I didn't reset it right away, each time it would drift. And if you set the strength, or the weight rather, of your IK constraint equal to 0, this target would start rotating. And so if every time we loop through this, first we snap it to the foot rotation and then we snap it to the ground, it's always basically zeroing out and then going back, as opposed to if we don't do that and we zero the weight, it seems to spin. It seems to just kind of add itself up. So we're going to first kind of zero it out essentially to the foot. And then we're going to use Euler angles. The local Euler angles. And if you don't know what Euler angles are, it's essentially, as opposed to an absolute, well, it's essentially describing the rotation of the axis in X, Y, and Z. You can look it up, or if you've been through some math classes, you might know what they are. But it is essentially taking an axis. So here you can see the X, Y, and Z axis here, and describing what angles it takes to be able to rotate that axis to equal a new axis, a rotated axis, but it's maintaining its origin at the same point. So here we can, rotate its Euler angle in the X first, and then rotate in the Y, and then rotate in the Z. So now this axis is no longer at all parallel with what we started with, because it's been rotated 3 times about these axes. And I'm going to zero that back out. So that's kind of a quick rundown of Euler angles. Pretty simple. So it's going to be equal to a new vector 3. And we are going to say the original target transform local Euler angles dot x plus now the angle about x. So now we're taking that original x and we're adding that new angle onto it to get that new x to be parallel with the ground. And because this is pretty long, I'm actually going to just go to the next line here. Dot local Euler angles dot y. We're not changing the y for now. I might in a future video, but he will just keep his feet as they are in the animation. I'm not going to rotate it in y. And then all target transforms I local Euler angles dot z plus that angle about z. Okay. Now we can go back here. We can hit play. And now let's move blue. His feet should be matching the ground pretty well. And then the angle should match as well. And look at that. He's, oh, okay. He's going to start floating away on me. All right, there he goes. Very slowly. You can see here now, just through that though, now it's matching this ground, which is awesome, which is exactly what we want. And then if it goes above it, it just goes back to his feet. He is All right. Farewell, Blue. Have a wonderful flight. You know, I implemented a flight in my script for Red here. He does not fly like this. It's a little more player determined rather than just, you know, floating. All right, moving on. So that's great. So now these targets all rotate. They're local Euler angles. So you can zoom in here on a target. Based on this sphere cast to the ground and the hit normal that it produces, it's rotating the X and the Z to match the ground below it. All right. Now the next thing we're going to work on is changing the weights of these constraints so that he can still walk around and his feet aren't stuck to the ground. Right now, if we change to walking testing, he just taps his toes like he's dancing to a beat. But he can't actually pick up his feet and walk unless you change these weights here. And because we put this into our script, now we can actually modify these weights via our script. But the first thing we're going to have to do is go to our animations. And here, these are all the animations that come with these with this dragon. We're going to go to his walk animation. I'm going to click on this. Actually, we'll click on the whole thing. And in each individual animation here, you need to go to curves. And I've already done this, so I'm not actually going to do it. I will show you real quick. I can just regenerate one. But if you click on curves here, you need to actually create a curve that matches each of the foot weights, quote unquote. So here, if I zoom in here, and I can actually, believe I can undock this. Convert to floating window. There we go. Let's make this a little bigger. Okay. So if I hit play here, you can see it going through the animation. And if we zoom in here on his right foot, basically what we want is when his foot is on the ground, we want the weight to be high, basically 1. And then when he picks up his foot, you want that weight to be basically 0. So right here, this is the front right foot, and here you can see on this curve it's 0. So I already went through because I did this for you know, a different model already. I already went through all of these animations and determined the foot weights based on the animation. But essentially, what you can do here, I'll add a new curve. We'll call this one curve test. And there's a couple of ways you can go about changing this curve. The easiest, it seems, is kind of marking the keyframes, basically. So he's picking his foot up right about here. So you can drag this line here to maybe right before he picks up his foot, add a keyframe. And then, you know, all right, now his foot is completely off the ground. So now add another keyframe. It's flying through the air. And then his foot smacks the ground. And that's actually right at the beginning of the animation. So we've already got keyframes at the beginning and the end we don't need to change. So now we need to go to here. And we essentially need to change these keys here. Change the values. So this is going to be 1. Oh, I forgot to hit edit. Or enter, rather. This is going to be 1. This is going to be 1. And this is going to be like 0.25. Let's see here. That's actually incorrect. Hold on, let's see here. So he picks up his foot there. Oh, there we go. Yeah, so this needs to be 0. Or, you know, very, very close to 0, but we'll do 0 here. So now this is essentially going to loop here, and I already I already created these curves. So actually the right front foot is going to look a little different. It should actually, it's going to look more like, I'm gonna add another key here. And I'm gonna take this and go up so that it can basically loop. Oh, okay, didn't mean to do that. But so now essentially, if you watch this curve that I just made here, you hit play for his right front foot weight, which is essentially all you're going to be doing is changing how much that foot is attached to its target. So when it's on the ground, you want it to be attached. When it's in the air, you want the animation taking over. So as you kind of walk along here, you can see this line following. When it's on the ground, this right front foot, it's going to be 1. And then as he's picking it up, it goes down. And now it's 0 in the air. And then it jumps back to 1 at the end of this animation. Cool thing about these curves is you can actually save them. So if I click on this guy, I go to this gear here, and then if I hit new, it will actually save it. So now if I say click on a different preset, and oh, I didn't mean to do that, so now I can go back to this other curve. And I'm gonna go ahead and delete it actually because I don't need it. And so that is how you have to do this for all of your animations. You need to create these curves. So for my walking, I'm having it loop between 1 and 0. For something like his idle animation, I'm actually having it loop between 0.85 and 1 and differently on the feet. And that's so that the animation can kind of pull the targets back a little bit if they start to drift. I found if you keep it just at 1 the whole time, even if he's just standing there, sometimes with the sphere casting and slight variations, the target will start to drift. So if you kind of have it loop between, say, 0.85 and 1, the animation itself can kind of drag that that foot back into position so that he's not, sliding all over the place with his feet. So you're going to need to do that with whatever model you have. You basically have to go through all of your, and it needs to be the this full idle import or full model and animation import, because you need this section in the inspector. If you just go to the animation itself, it's not going to allow you to do that. You need to have the full thing with the root model, root and mesh and everything all together, and then you can change these. Once you do that, you can go to your animator itself, and I can actually open this up. So I've already created this. He starts out with his ground movement. This is a blend tree. If you don't know what a blend tree is, you can look it up. It's essentially taking, based on an input, and here I have the velocity, it blends between different animations. And so I have at 0 velocity, he's idle, and a little bit of a threshold here, and then he's walking, and then he's running, and then he's running a little faster here. So this column, you can change that animation speed. So all of these different blend trees and animations here have those curves involved with his with at least when he's on the ground and he's not flying. And then you need to create floats that are based on those weights. And so it will actually take from that animation, as long as you spell it right. So here, this says RF space foot weight space, or space foot space weight. And so then if I go back to my animations and I click on walk, it says RF space foot space weight. So you need this to be identical to what it is in the animator. So then you just need to pull these into the animator. These are all floats. And then these can then be taken from this animator, pulled into the script, and then used to change your weights that you have in your rig. And that's what we're going to do next. So we need to pull that animator. So we'll do another serialized field. Animator. And we'll just call it animator. Let me save it, go back to Unity. And now I'm going to change it to his, actually we'll keep it walking testing for now. But now here, for his animator, all you have to do is actually just drag this in. And so now it's taking the animator component from blue here. So once we've got the animator inputted into our script, we're going to create another array. And these are going to, it's going to be a float array, I believe. Yeah, it's going to be a float array. And these are going to be all the foot weights that we're going to pull from the animator and then input into our script and change each of the rig's weights based on the animation curve that we created. So we're going to call it all foot weights. Okay. And then down here, we just need to initialize it. All foot weights is a new float, and it's going to be size 4 for our 4 feet. Okay, so now in our method here for rotating the character feet, we're going to take each of our animator dot get float. We're going to take each of the floats that we defined in the animator based on our curves, f foot weight, and we're going to import them. All right. And then here in our for loop, all we have to do is call our foot constraints rig setup, or constraint setup, I suppose, for each foot. And then we can go to weight. And all we have to do is set that equal to all foot weights dot I. And actually, I don't even know if you have to do that. Let's see here. Hold on. So each time this method is called here in the fixed update, it's going to update our array here, and then update the foot weight, or rather the constraint weight for each of the feet. So I can show that real quick. I've opened up the right front, and here you can watch this, and I'll zoom in. But as he's walking, you'll notice that foot weight is going from 0 to 1 as he's walking. And so now he's actually able to, even though he's still got this target in place, he's able to do his little walking animation, and it automatically updates this weight based on our curve that we put in manually earlier. One thing that I noticed in my kind of experimentation setting this up is if you only change this weight and these are all 1, he kind of gets this like stickiness effect, like he's walking through mud. What I found is changing this value to like 0.75 makes it a little better. So you can see here now his right front, if I go all the way up again, You see how he's sticky there, and as I lower it, it gets a little better and a little better. In my experimentation, I believe I set it to about 0.75. And that combined with some other stuff that we're going to do here momentarily, it'll look pretty good. So I've gone ahead and changed all the position weights to 0.78. From my previous testing, that seemed to work the best in terms of keeping the foot from sticking too well to the target if you're walking around. And that combined with the weight, you get a relatively smooth animation while still getting the right heights and rotations. Now, that does cause us a new issue, though. If he's sitting here idle, if you bring him to the edge of a short little drop here, and then you have him just stand here, because those position weights are lower, now his foot sinks into the ground, and we don't want that. Even though you want the position weight to be 0.78, so that when he's walking around, it looks good. You don't want him sinking into the ground if he's just sitting here idle. So we're going to come back to our script. First thing I'm going to do is actually take this here. I'll take the whole thing, copy it, and I'm actually going to define it here, as well as include an if statement and say if the foot, if the foot transform position.y is less than the target transform, given a little bit of wiggle room. If it's less than that, now the y offset is going to be adding this new, this difference between the foot and the target. So we're essentially canceling out the foot sinking into the ground by now adding that height into our offset. And the and you have to remember this foot transform, even though I call it foot transform, it's starting at basically the base of the ankle. And so if you think about it, the base of the ankle should never be below that target transform, or else it's going to be sinking into the ground, because the target transform is always going to be just above the ground and originally plus this little bit of offset. Now, if the foot starts to sink into the ground, we're going to add that difference in here and then change our target transform here. So now we can go back over here. You can hit play. And so now you can see these target transforms moving up and down, and that's partially based on our weight changing here. And keep in mind, this was to keep the feet from kind of starting to slide around if he was idle. At least that's what I found with my own code testing, is his feet would start to slide around. But now his feet are no longer sinking into the ground. They're wiggling just a little, but barely enough to be noticeable, which is great. Okay. So now I believe, I'm going to check my other code here. I believe that's really all we need for our foot transforms and our rotating and moving the feet. So let me actually start this, and I'm going to move blue around while the game is running. And his feet should adapt to wherever he is. Okay, so we're going to move him over here. Oh, okay, so he's got a foot up here on the side. Maybe in a future video I might include a way to, if it's too high or too out there, do maybe a cube intersect for positions such as when he's like, I mean, it looks a little strange, but it could work, depending on the look that you're going for. But here, let's pause here and let's move blue over here. And we're going to do kind of a wiggle test here. So I've got this wacky terrain. Let's unpause. And now look at that. Besides maybe his back feet, they're wiggling just a smidge. It looks like it's kind of getting at the very edge of his range here. But overall, and I can move him around and he'll update automatically. Overall, it looks pretty decent. You know, if you're out here, you know, third-person game or whatever, and he's moving around. Oh, and he's not sinking through the floor. It looks pretty good. His feet and his legs are now turning and alternating and moving to match the terrain, the height, and the angle. Okay, so next I'm going to be working on the body. I don't know if I'm going to actually do a different video for that and separate it out, or do it all in one huge video. But I'll show you why we want to be able to rotate the body here. So if I move him to one of these more extreme slopes over here, you will very quickly see what I'm talking about. If I just double click on him. So if I unpause, so now look, he's on this slope, which is great. And if you want him to, you know, be able to always look straight ahead, that's okay. But you can see here that he is kind of maxing out his leg length. And if I move him to one of the more extreme slopes, you can kind of see what I'm talking about a little better. It looks a little unnatural. His back feet are all bunched up. His front feet are actually, you know, very close to, this one is definitely maxed out the leg length here. And that's not really what we want. So we're going to be implementing some code that allows us to rotate the body of the whole character now to match our slope. And now he's going to just spin around because he's got no control on him. Wow, that was very majestic, Blue. I'm proud of you. But we're going to be changing his character rotations, which will rotate our capsule collider here as well. That way it's not rubbing, you know, the front edge of it up the whole way. It'll be like he's running on flat ground, but to, you know, the world, he will be running up or down a slope. Hey everybody, in the last video we were setting up IK constraints for our four-legged little dragon here using the animation rigging system, and we finished putting the position and rotation of each target for each leg based on the ground below it. And so in this video we're actually going to be rotating the whole character body so that if he's running up a heavy slope or down a slope, his body will actually rotate to match the average of each of his feet, you know, the ground below his feet, each of the normals. That way it looks pretty natural in most situations. Okay, so I'm going to create a new method here. Private void. We're going to call this rotate character body. And then we're going to take this method and we're going to apply it just after our feet in each fixed update. Okay, and we already have almost everything that we need based on when we were rotating character feet to get this body rotation correct. So we're going to start out and we're going to define the maximum rotation that the character can turn. We don't want him unless he's climbing on walls, and you can implement this yourself, but we don't want the body of the character to be rotating to extreme angles to, like, you know, 90 degrees or something. So I'm going to define a max rotation x is equal to 50. And I gotta do a float here. And the z is it's going to be about 20. So if he's running up a hill or down a hill, he can rotate about 50 degrees in either direction. If he's sideways on a hill, we don't want that too extreme. So right now, and you can change this, however you want, but for me, I'm going to have it to be 20 degrees. And this will be plus or minus 20 degrees. Okay. Now we want to define the character X rotation, and that's going to be equal to the transform dot Euler angles dot X, and another float called character Z rotation. And this is equal to the transform dot Euler angles dot Z. And that's just getting these Euler angles so that we can modify them as we need. Okay. Now, real quick, because of the way that Unity is set up, in the editor, if you look at his rotation here, and say if I rotate him this way, it goes negative. And then if I rotate this way, he goes positive. But in the actual script that we're writing, when we get the Euler angles, this is going to be a number from 0 to 359.999. It never goes negative. And for our math here, we just want to fix that. It can interpret a negative number. If we add, if we take this transform Euler angles and subtract 10 and it started at 0, it will put it to 350 degrees. But for our math here, we want it to know if it's a negative 180 or a positive 180. We don't want it to wrap around because 0 is always going to be flat with the, with a flat plane. And so if we're doing, plus 20 degrees for, at least for my own sanity for the math, plus 20 degrees and minus 20 degrees, a little bit up or a little bit down is a lot easier to understand and work with than doing plus 20 degrees, 340 degrees. You don't have to do this if you want to, finagle the math a little differently, but I'm going to do it myself here right now. So if the character rotation X is greater than 180 degrees, we're just going to subtract 360 from it. So now we're going to get a negative number with this. And then we can do the same thing with the character Z. Okay. And all this is going to do, if it's greater than, say if it's 181, it's going to subtract 360 degrees. And that's going to give us negative 1. Or I'm sorry, not negative 1. It's going to give us negative 179. There we go. And so say if it's 350 degrees, and it's going to subtract 360, then it's going to give us negative 10, which, is 10 degrees, down. Okay. Next, what we want to do is, let's say we're on a slope, and we'll get here momentarily, but let's say we're on a slope here that is greater than our maximum rotation. We've got our little character, and let's say over here, for whatever reason, our testing slope or an actual slope here is greater than the maximum amount that we want to rotate our character. We don't want this thing to just stay at 0, so he's rotating nicely up until our max, and then he just snaps back to 0. We still want him to get to his maximum rotation. So we're going to go to our code and just set this up here. And we're going to say if the character X rotation plus our angle about X is less than our negative of our max rotation X, we want to now set the new angle about X. And I actually need to set this earlier. So we're going to actually define a new angle about x each time we call this for this script. But for now, I'm just typing this in. So our new angle about x, just going to do some quick algebra and move those around. We're going to take the max rotation x. We're going to subtract the character x rotation, and that's going to be our new one. Else if our character x rotation plus our angle about x is greater than our max rotation x, the angle about x is going to be equal to the max rotation x minus the character rotation x. Okay, and all this is saying is if the current rotation of our character plus the angle that we want to add on to that is either then less than the negative or greater than the positive, then we just want to set that new angle we're going to rotate equal to the amount that it takes to get to the maximum rotation. And you can write this up yourself, but it's essentially like if our maximum is our 50 here, our character is rotated 20 degrees already, and we're wanting to rotate it an additional 31. That's going to be, and it would actually be here, an additional 31. That's going to give us 51. So instead of that, our new value is going to be 50 minus 20, which is equal to 30. So that will then rotate our character to 50, which is our maximum. And we're going to do it same for the z. Okay. Oh, did that too early. Else, if the character rotation z plus the angle about z is greater than the max z, then we want our, and that needs to match. There we go. Our new angle about z is going to be equal to the max rotation z minus our character rotation z. Okay? So now, no matter where our character is currently rotated and how much we're trying to rotate him, it will only ever go to the maximum. Okay, now I was already talking about our angle about z, but we actually need to define this for the character. It's no longer each individual foot, which, this is what we were using up here for the feet. Now we need to describe our rotation that we're trying to move the character as a whole. And how we're going to do that is we're going to first set up average hit normal x and start that equal to 0. And we're going to do that twice more and do a y and do a z. Okay. Now, because we've set everything up already when we were doing the feet, we're going to set up a new for loop to get the average of all the hit normals per fixed update. And I can set that up right now. So the average hit normal x is going to be plus equals, and it's just going to be 0. Starting off with 0. Average hit normals, and the I, because we're rotating it through, or we're looping through each time to get all 4. But we're going to do this for each one. And all this is doing is taking the hit normal from each individual foot, and now we're going to average them all together. And I need to change the name here. There we go. Okay. And now our total av hit normal, and I actually need to define it up here first. Give it a vector 3. This is going to be a vector 3. It's a normal vector. Private vector 3. Hit av, hit normal. So this is going to be the total. So this is going to be equal to a new vector 3. And we're going to take the average hit normal x, going to divide it by 4. Average hit normal y, divide this by 4. And average hit normal z, and divide that by 4. So we've taken all the hit normal x's, all the hit normal y's, and all the hit normal z's, added them together, and then averaged each of them, divided it by 4 for each of them. And then just to make sure, we're going to normalize it as well. Okay. Now we have the average hit normal for each of the feet all together for the character. Because if the character's body is over a weird rock or something that's angled differently than, say, if he's just standing on flat ground, but then just over the center of his body is just a rock. We don't want a sphere cast down onto that rock, get a funky angle, and then he's standing, sideways on the road because he happened to be standing over a rock. We're actually going to take each of the feet and then average them together so that even if he is standing over a rock, but all of his feet are flat on the ground, he's going to be parallel with the ground. So now we're going to use our projected axis angles method that we created earlier. We're going to do a new x, a new z, which we wanted to use earlier. We need the transform, and we need now this average hit normal that we're going to input there. Okay. Okay, now we're going to determine the new Euler angles for the character and just apply it to the character. So we're going to define a body Euler x, and that's going to be equal, and we're going to use the move towards function and move towards angle. And all this function does is take in two values and an increment. So you could say 0, you're starting at 0, you want to move to 1, and you're incrementing by 0.1. And so each time it loops, it's really only going to, move that to 0.1 each time. It'll reset every time. But for our case, we're going to take in the current rotation of the body where we want to go, and then our maximum rotation per fixed update that we want to allow. So we're going to start off at 0. We want our new angle about z, or x, sorry. And then we want a max rotation x. Oh, I'm sorry, max rotation step, because this is going to be different than the feet. And I believe I should have defined this already. Let's see here. Sorry, I'm looking over at my cheat sheet trying to find why I didn't already define this. Oh, I did. Okay. So we're actually just going to take this. We'll just define it in here. You can define it, I suppose, wherever. But we'll rotate 1 degree per fixed update. That's fine. Okay. Now we're going to do the same thing for the body Euler Z. And you could be asking, okay, well, why are we, always starting at 0 and trying to move towards our x? If x is 20 and we're only allowing it to increment 1 every time, it's always going to go back to 0. But we're going to be adding this onto the body. So every time we do, it's going to be changing this as well. So if we start at 0 and we want to go to 20, next frame, we're going to start at 1. And so our new angle that we're trying to rotate to is going to be 19. And so it's really, technically you could do like just this body Euler angle x is just equal to this max rotation step. But the reason I'm setting it up like this is eventually when this angle about x is equal to our body rotation, then it's no longer going to be moving towards anywhere. It's going to start at 0. It's going to move towards 0, and then it will add 0 to the body Euler angle, which is fine because, it's not doing anything. You could set it up a different way. This is just how I decided to set mine up. So now our transform dot Euler angles is going to be equal to a new vector 3. And now we want the transform dot Euler angles dot x plus our body Euler x transform dot Euler angles dot y. We're not adding anything because really this would be determined by the player moving around with WASD, mouse, etc. So that's going to stay. And then transform Euler dot z plus angle about z. Okay, and that is, as far as I can tell, everything we need. So we're taking in our hit normals that we got from each individual foot, we're averaging them, and then we're now taking this, we're projecting our character transform, so the characters x and z, onto this new averaged hit normal. That averaged hit normal is going to form its own plane, essentially, which we will then project the x and the z on there, and then we will get how much we need to rotate the x and the z to put them onto that new plane, and then we're just going to rotate the character's body based on those two angles. And let's try it out and hope I didn't mess something up. And look at that. And that was, not a super complicated piece of code, but now it looks really good. His body is rotating to match there, and now I can drag him up the plane. And now that he's half on the top and half off, and he's kind of sliding around here because he's got no control and very little friction. But now he's like slightly angled down a little more because 2 of his feet are flat and the other 2 are angled up, which is perfect. So now you can actually take him to any slope that you want, and his feet, oh, all right, there we go. He's stuck. Oh, no, he's just going to freak out a little bit. Cool. Let's move him out of there. Now his feet and his body are going to rotate to match the slope that he's on. And that wasn't actually too difficult to implement. Okay, so now I'm going to actually minimize this as well. And I'm going to minimize it on my cheat sheet. Okay. All right, so one last thing that I wanted to do, and that I've done on my other character, is actually move the capsule collider up and down based on the average of the feet. And essentially what we're trying to do is, if he's, say, on the top of a sharp peak, but his feet are all around it, it's going to be a very different looking scenario than if he's at the bottom of a crevice and his feet are kind of mushed up against him. So here I can start this and I can show you what I'm talking about instead of telling you, which is much smarter. All right, so let's pause this here. Let's move him over here. All right. So if I unpause this here, we got his feet and his body to match the rotation, which is fantastic. But see the difference here. So here he's kind of, relatively close to the ground here, which is fine. But then if I take this same capsule collider location and put him on top of this peak and unpause it, now it's a little different. And you could think of extreme scenarios. If you're never moving this capsule collider at all, it may work fine for flat ground and, maybe gentle slopes or something like that. But if you're ever going to have your character standing on top of sharp peaks or at the bottom of a crevice, which, players are wont to do, they just want to go wherever they please. You don't want him one extreme, if you get one extreme looking good, then the other extreme is going to look terrible. If he looks fine at the top of a peak here, let's say if I get his capsule collider real close, his body's real close to the ground and his feet look fine, but now I move him to the bottom of a crevice, now his feet are all jank because his capsule collider is really, really low. So what we want to do is raise that capsule collider up so he's actually standing on the crevice or the peak, wherever the player is. Okay. So, and we are going to create a new method. I'm going to call it character height adjustments because I, for some reason, like really long method names that are self-explanatory. And we're going to call it as well. And essentially what we're going to do here is we're going to take the average height of each foot and compare it to the height of the body. And that is kind of the reason why back over here, I wanted to take each of these IK constraints and set it to 0, 0 on the character body, because now we're going to be using these Y values of the targets to compare to that original placement value, because it's local Y value is what we want. We don't want the absolute position. We're just going to use the local, which is why we want it zeroed out on the character. So if all of these targets are too low or too high, like we had on the peak or inside of the crevice, we can adjust the capsule collider automatically. And I keep bumping my desk by accident. Okay, and we want to actually define a couple of things here. We're going to do serialized field. We're going to create a range. So we got a nice little slider here. And I'm going to say negative 0.5 to 2. It's going to be a float. And we're going to call this upper foot Y limit. And the starting value we're going to set to 0.3. And we're going to call a lower foot limit. And our values are going to be negative, oh, I need to do F there. Going to do negative 2 to 0.5F. And these values are essentially defining what we consider acceptable for how high or how low the foot target is. And eventually we're using the foot targets and not the feet themselves, because as he's walking around, his foot's actually changing quite a bit. It's up near his body when his foot's off the ground, and then it's against the ground when his foot isn't. And so we just want the actual target, because that's going to be where the ground is, or at least very close to it. And these values are just what our upper and lower ranges are. And we made a serialized field so that you can actually just do, in situ alterations here. If you're seeing that, oh, he looks fine, with the upper limit, but the lower limit, he just looks way too wonky. It's too strict. And so we're gonna extend that a little bit or something. And you could do a serialized field for really any of these. You want to change the max hit distance on the fly to be able to tell what's going on. You can also use draw gizmos if you wanted to check your max hit distance and added height. You can draw a line or draw a wire sphere for where our sphere cast is or whatever. Plenty of people have tutorials on how to do that if you wanted to. Okay. Okay, for this, we're going to do another for loop and use that same int I. Loop it 4 times and add it to each. Okay, so for this, we're going to be checking each foot. And from my own personal experience, experiments, I found that raising and lowering this, you can do either strict, where you're comparing every single foot and you want to know if all of them are too high or too low. Or in my case, I'm actually going to do opposite feet. So essentially, if this back foot and this front foot are both too high, in 99% of scenarios, that's going to mean that he's a little, the capsule collider is too low and we need to adjust, and same with these opposites. And you're going to set an or statement. And we'll type that in. And I didn't mean to do that. Plague is my potentially placeholder. I don't know yet, but that's the name of the game that I'm trying to develop, and what I've been working on as I've been making this script, in case you were curious. So if the all target transforms I dot local position, because we want to compare to the parent, which the parent is zeroed on the character ultimately. So y is less than our upper foot limit, and the target transform is greater than our lower foot limit. We don't want to do anything. That's our initial condition. And I'm actually going to use a check here. Local target y. And this is just going to be it's going to be an integer, and it's going to be basically a 0 plus minus. So if the foot is too high, it's going to be 1. If it's too low, it's going to be -1. And if it's within our range, it's going to be 0. And we're going to use that to, it's like kind of like a Boolean, true, false, but since there's 3 values instead of just 2, we can't really use a Boolean in this instance. So I'm going to define a new private integer. I'm going to call this check local target y, and then we'll initialize it here. Check local target y is equal to a new integer, and there's going to be 4 of them. Okay. Else if, and then we're going to do one extreme if it's too high, and then the other will just be else, because if it's not within the range and it's not too high, then naturally it's too low. So all target transforms I dot local position dot y. We're going to do greater than the upper y limit. We're going to set our check for this, and that's going to be equal to 1. Else, oh yeah, and just for my own sanity, I'm going to put that there so it looks nice. And then if it's not that and it's not the other, it's going to be equal to -1, meaning it's too low. Okay. And now actually, outside of this for loop, so now we've gone through, and for all 4 feet, we've checked is it within the bounds, is it too high, or it's too low. Also, because it can get a little confusing thinking of, is the target too high, or is the foot too high, or is the body too high, whatever. I like to think of the upper foot limit. If it's surpassed, then it's actually the arm is, or the leg rather, is being like squished up against the body, and the lower foot limit, if it is surpassed, that means he's like, his foot's stretched out as far as he can go. So I call this squishy arm, or rather squishy leg, and this is stretchy leg. Easy to remember that way. because upper and lower can get confusing. And to be honest, if you wanted to, you could change this to upper, or I mean, you could change this to squishy and this to stretchy for fun. We're going to set a new if, and now we're going to be checking each of these. So check, target, and we're going to check the right front and the left back, you know, the diagonal there, or the left front and the right back, the other diagonal. And if this is squishy, and this one is also squishy, or this one is, oh, I'm sorry. This doesn't, you don't want this to be 0. If that one is squishy, or if, and this is going to be the left front, if this one is squishy. So if any of those options, then we're going to take that capsule collider and going to bring it down in relation to, or I'm sorry, bring it down into relation to the character so that the character model gets pushed up. Lots of local positions here, which can kind of make it confusing on what you're trying to actually do. And we actually need to get our capsule collider here. So we're going to create a new, and I guess we've never really used this so far, so I'll just comment this out for now. So it stops complaining. So private, and this is going to be a capsule collider. Oh, and call this capsule collider. Did I already define this? Am I getting behind myself or ahead of myself? I don't think I did. No, okay. All right, now we're going to be defining this capsule collider. So here, capsule collider is equal to, we need the character here. I think we could just say get component. Capsule collider. Yes, okay. So because we put this script on the game object that also has the capsule collider, we can just use our get component. We don't have to call anything to get the component. Okay. So if they're all squishy, then we want to do capsule collider dot center. And we want to move it down a little. Okay. Goodness gracious. Sometimes the IntelliSense just goes bonkers if you accidentally mistype. Else if. And now we're just going to take all these and say if they're all stretchy, then move it the other direction. So is equal to -1, -1, -1, -1. And we're going to do capsule collider dot center is equal to plus equals new vector 3 0f 0.05f 0f. And to be honest, doing the movement like this is kind of the other option. So here up in the character body. In the character body, we did a math move towards the angle about x and the angle about z and moving it this single direction. And the reason I did that here, explaining it to myself, I suppose, was so that you could, as this was always changing and as it rotated closer and closer to where you wanted to go, this angle would get smaller and smaller and smaller and eventually reach 0. The other way we can do it here is just continuously add it, but then we need an if statement because then we need to include the limits. Otherwise, say, for example, I'll save this here. say we take this. Oh, hit layer. Oh, I'm sorry. I shouldn't have commented this. Uncommented this. There we go. Now it. Okay, there's a reason why I put that in there. Okay. So now here, what happens is, if it gets slightly too low, it will continue to fall. So now there's no lower limit here. So we need to set this lower limit. And we could do it, in my case, one of two ways. You can either set a math move towards and give it an upper limit. And so as it moves closer and closer, once it gets there, it's just stopped moving. Or what I want to do in this case, and I keep clicking on that, I want to have an if statement. If it goes too low, reset it. That way, if the capsule collider ever does happen to get below the Earth and then it starts just going away on you, then you can reset it to the character position. So we're going to take this here. We're going to actually say if capsule collider.center.y, and I'm going to say is greater than negative 1.4. If it's greater than this value, and that's just what I got from my own testing, then you can keep, continuing to subtract it. If it's not, then if it goes below negative 1.4, that means it's gone too far. The character is now like ragdolling on the floor, and you can put a capsule collider on like the spine just to make sure that it's not, moving around below the Earth if the capsule collider gets too far. But if it gets below that value, then we want to reset it. So capsule collider.center is equal to new vector 3 of 0, 3.4f, and 0f. Okay, and we'll do another limit here, just the same. So if the capsule collider dot center dot y is less than 1.5, then you can do this. Okay, and all that's saying is if you are not past the body, then you can keep adding on the here. So I can go back to here. I can uncheck that. And so essentially what I had done, and I can simulate this here now that he's frozen. I essentially did, all right, I moved the capsule collider up to his body. That's 1.7. And I believe I had set it to 1.5, so a little bit conservative. I'm an engineer. I have to add tolerance onto everything. And then if it's below this negative 1.4, which is pretty low, I mean, this is actually pretty extreme. But if you move the feet, it gets pretty close on this model. If it's below this, then it's going to then go back all the way up to here and then reset. And actually what we do want to do is go to his spine, add a component, and add a capsule collider onto it. And for some reason with this character, his scale at his root is 0.01. And so everything on top of it, that scale gets applied to everything. So now watch. This capsule collider here is, its radius is 0.75 and its height is 3. Now this capsule collider that I added, watch how large I have to make this in order for it to even show up. I need 155 height to get it to be that large, just because for some reason when they were making this character, they made his scale tiny on the root. And then I'm actually going to take this and change it to the x-axis. This way he has a, nope, didn't want to do that. I want to just move this slightly. This way he's got something that prevents him from falling through the floor if his capsule collider gets too low. And I did, to be honest, I did try putting capsule colliders like in his feet, in his legs, and in his spine, and then getting him to walk around using this script. I couldn't get that to work. I might work on it some more so that you don't have to have this central capsule collider. You can just have a, you know, these capsules on his skeleton here. This is just what I've gotten to work at this point. So now, if we hit play, so now he will, you know, rotate to match here, and then if I try and force him into the ground, there we go. See, did you see what happened there? So you just watch this capsule collider. If I force him into the ground, his capsule collider starts going down, and then it just kind of resets. So it kind of looks like he like takes a nap for a second. And then because of the way we set up the code, once it's above and his feet are still too low, it will continue to adjust until it is correct. And you can, you know, bring this guy over to a crevice, test it out. So let's see. Just double click on him there. So here's what he looks like on, you know, down here in this crevice. He's no longer super low to the ground, but I can move him over here to be on top of this peak. And there we go. Oh, and he's, of course, he's going to rotate around because his friction's really low. But let me actually get that to work so that you can see, and I'll actually freeze him when he gets there. Boop. There we go. So notice how now his capsule collider is automatically adjusted up. And so he looks a little more natural. He's not like all stiff-legged on top of this crevice or on top of this peak, even though he looked pretty natural here too. And that's because we were averaging all the target heights in comparison to the body. And we wanted those local heights because if he's rotated, his local Y is still going to be up in terms of the character, not up in terms of the world. Because I found if you put him on these large peaks over here, which we can do, change to movement here. So if I unpause him here, get him to stick. Oh, and he's kind of freaking out there because he's on two slopes at once. There we go. So if he's on this slope and you're checking the absolute Y position, even if you like subtracted the character's Y, these would be below, but these would be above. And this capsule collider would have no idea what to do. But because you're using the local Y has been rotated. It should be. Let's see. Nope, I am grabbing a different Y. Am I on red? I am on red. Oh my gosh. That's what I get for having two identical structures in the hierarchy. So here, this local Y is still the same if it's on the slope versus if it was on the on a flat surface here, and I can prove that. So his local Y here is 0.28, and if we take the character, move him down the slope, let him readjust to the ground, boop. Check this again. It's about 2.4, barely different, and that's probably just his you know, his idle or something. But yeah, now this is why we were using the local position, because we're rotating the character. We can still use this as a comparison to his body height, and we don't have to use the world position Y, which would give you weird answers if you're on a slope. Okay. And I believe, let me check my cheat sheet here. So there are a few things that I'm still working on. Moving this capsule collider, it's a kind of rough approximation of what I want. Ultimately, I want a character to be able to, do maybe something like a mesh collider. I haven't worked with mesh colliders yet, but for my purposes at the moment, this works pretty well. But there are a few things you probably noticed earlier in parts of the video that if the maybe the maximum distance on that sphere cast from the foot was slightly too long, he could hang over the edge of a small cliff and his foot would just kind of float in the air. I've attempted to work on rotating the character based on that so that if he was hanging off the ledge, he could rotate down a little bit to get his feet back on the ground. I think I'll keep working on that. I don't have that fixed yet, but I may make another video once I do get that fixed. So I believe, and let me close these. I believe that's really everything that I have for this tutorial here. Ultimately, if you followed this tutorial and you have a movement script, you should be able to get a character that can move around and walk around and automatically adjust to whatever slope he's on. There's a little bit of lag here. I have a snap to ground feature, but he's a little floaty. Still working on that. But the general purpose of this script is, it's working pretty well. The floatiness of the character is a totally different issue. But now I can move him around. I can turn him. I can get his foot to be up on the ledge and he can look all goofy. I can have him run up this thing and he'll rotate and go stand on the top of this thing. And that is exactly what you want. Oh, there we go. So yeah, this completes the tutorial. If you did learn something or you followed me all the way through, I think this is probably about an hour and a half at this point. I very much appreciate you, and I hope this helped. Even if you didn't follow me exactly, maybe it gave you some ideas or something like that. Please leave a comment if you have constructive criticism or if you have praise. If you did like this, I'd really appreciate it if you left a comment or like it or spread the word or whatever. And hopefully I can make some more of these as I progress in my own Unity knowledge. If I don't see, helpful tutorials for something that I'm trying to work on, and it's not overly complicated, it's not super specific to one game that I happen to be making. If it's more, general like this, if you have a four-legged character and you want him to be able to walk and adjust to slopes and different heights and terrain, then I'll make some more tutorials. So again, thank you very much, and I hope to see you later.